Using his laws of motion and his universal law of gravitation, Isaac Newton was able to derive all of Kepler's laws. This gave us a deeper understanding of what made the planets orbit in the way they do. Newton also revealed the universality of Kepler's laws. That is, Kepler's laws not only apply to planets orbiting the Sun, but equally well for moons orbiting planets, stars orbiting galaxy centers, galaxies orbiting each other, artificial satellites orbiting the Earth, etc. Newton's derivation of Kepler's third law was more general and more complete. Newton showed that masses were involved. The equation shown have the familiar cube of the semi-major axis, A, and the square of the orbital period, P, but it also has the sum of the masses of the two objects in question. That is, if one mass is orbiting another, the sum of their masses is equal to the semi-major axis distance cubed divided by the orbital period squared. There are some additional constants involved, but if we always have the period in units of years and the semi-major axis distance in astronomical units, then those constants all come out to equaling 1 and do not need to be included. This simplifies the equation. Suppose we observed a moon orbiting a large planet. This form of Kepler's third law allows us to measure the center-to-center distance between the planet and its moon, measure the moon's orbital period, and then calculate their combined mass. If the planet is substantially larger than the moon, then the sum of their masses is basically just the mass of the planet. In other words, we can determine the masses of planets, stars, galaxies, etc. by simply measuring orbits and orbital periods. This is a very powerful ability that will be used time and time again in the remainder of this course.